Yeah. Yes. So as I said, the plan is here that, so what have we done? So we have looked at we have looked at linear functions. Yeah, I've looked at these functions. So linear functions, not just from R to R. Okay, we have obviously all of us know this. I mean, all of us knew this database, but also general things like maybe R2 to R2 or R2 to R3. Okay, R3 to R3 also situation is similar. So we have looked at linear functions. Okay, I'm not going to again say why the word linear and what are the various nuances in that and what all we had done, but I'll just give the definition once. Okay, that if you have the, let's say, just putting this notation for vector, if you, and this is just a scalar, okay, then this thing basically splits. So the application of the function f, which is a linear function, and the application of addition, okay, they commute. Okay, so it commutes with the linear, basic linear operation of addition. So, and also the scalar can be pulled out. We have analyzed these functions, okay, and we have seen that these functions can be represented by matrices. Okay, so these can be represented, and that was very good because that helped us to prove a lot of things about these functions, and that will also help us to prove a lot of things about matrices in the future, wherever you do linear algebra also later. Right now we are not doing proper linear algebra because that's not there's no need to do that now. It's not useful now, maybe, to do in that abstract way, but the spirit is the same in some sense. Okay, represented by matrices. Okay, so this we had seen. Okay, so basically what do I mean by, so let me just, I'll not say how we did this obviously, but what does it even just, what does it mean to be sure? Basically we are saying that if this function f, so if there is this function f which is taking v, so v will be like some column vector, right? And it goes via f and it goes somewhere. I mean, you can say a1, b1, c1. Then you see there is also a matrix. For f, there is a matrix. Matrix M, or let's say matrix A. There's a matrix A such that it does the same thing for all. I mean, there's one matrix works for all vectors, obviously. So this matrix does the job of this function. Okay, that was the thing. Okay, and yeah, and the main thing we had proved, right, kind of, is that so how do I say it? Yeah, is that, okay, let me just put it like this: injective and surjective are the same things, right? So this is another thing which we had proved. Okay. So now today we will try to see how we can use this theory of linear equations and its connection with matrices, how we can use this to understand, I'll just say understand, I'm not saying solve, okay? System of linear equation, because there's much more than just solving it. System of linear equations. We'll only do till 3 by 3, but the way we are doing, you can easily generalize it. Okay, but that's all. The goal here is to understand conceptually the matrices and theory of determinants and matrices that is done in high school, but understand it conceptually. Okay, so that just that understanding you can use in all places. So system of linear equations, we'll try to understand. So what kind of things? Basically, we'll try to say, when given a system of equations, just looking at the system, how can you say whether it has a solution or not has a solution? How many solutions are there? In some sense, we'll try to describe. And maybe also an efficient way to solve it without taking determinants. The determinants is not an efficient way to solve. Okay. And as a byproduct of these things, we will also understand some combinatorial meaning of matrix multiplication. Combinatorial, or not combinatorial, just combinatorial view of matrix, which will again is very useful in problems. I'll just also give a problem. Maybe if we get time in the end, maybe a few problems. Okay. And other things will come along. I have not planned everything, so we'll see. But this is a rough plan. So any questions before I move on? Okay, so then let's move. Okay. So let us start with a 3x3 system of linear equation. Okay. And let's try to see how we can interpret it. So let's say we have this. So I'm not going to go too much into the geometrical picture today. Okay. Otherwise, there will be too many things, too many. It's all very good to hear, but don't want to do too many things. So we'll just try to, when we look at a system, we'll try to connect it with what we have done about linear functions and matrices and so on. Okay. Not going to the geometry. The geometrical picture also very good and also can tell you a lot of things, but let's just say that we have. I'm just starting with homogeneous ones, meaning that the constants will be 0. Okay. There is also a good reason to do this. We'll see that. 3x. So I'm just writing an arbitrary. I don't know. Okay. Right. So if this kind of equation is given to you, and let's say the question is solve. Okay. Then how would you usually go about doing it? Anyone? Okay. 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 So that is rough idea. Okay. Okay. So before I dig into what he has said, let me just make this more precise. When I say solve, I am asking find all solutions. Okay. Yeah. Find all solutions. Okay. So let us say that the equation, I'm just naming the equation so that I can try to describe what he has said. I mean, all of us know what Raghav has said, right? Is we take some equations and we maybe add 2 equations or subtract 2 equations, right? So essentially what you're doing is you have, maybe if there is a step like this, this is a step 1, maybe you do equation 1 minus equation 2, right? Let's say this is one natural step. So my question to, I mean, you can understand why, because it will kind of maybe remove one of the variables. Okay, maybe remove the variable z, for example. My question is, how do we explain the legality of this? Why is it correct to subtract 2 equations? What does the question even mean? Why is it correct? Any comments on that? Have you ever thought, when I'm subtracting 2 equations, I'm just following some rule, right? But what do I have to verify? Why does this rule work? Or I don't, yeah. No, so that is right. That is certainly no. So that is what it does. But is it legal to do it? So what do I mean by is it legal to do it? What I'm trying to say is, let's say No. So that part is legal. I mean, what equations you get are certainly okay. They're certainly, yeah, that's right. That's right. But my question is, are we okay? So let's first do it. Then I'll start ask the question. Then I'll say what I mean. Let's say let's say we change the second equation. So that I should really write like 2 becomes 1 minus 2, right? 2 becomes the second equation now becomes 1 minus 2. So that's not good. I'm just writing 0 z. You see, you had one system of equations, and now you have, but this is a different system of equations, right? Now I need to guarantee that they have the same solutions. That is a fundamental question that we should ask. It may have a very simple answer. Okay, I'm not saying it has a very simple answer. Everything is simple, but why do A and B have the same solutions, or do they? Why do A and B have the K times? What do you mean by K? Yeah, that's true. That's true. K times that will be solution. But so yes. Yes. We want them to have the same solutions. Yeah, that's what so that is kind of encoded in this, that they have the same solutions. But yeah, but that is actually the key thing, because already what Raghav has said is that any solution of system A is a solution of system B. Exactly. And that's also not difficult, but someone should explain that to me. Why? Yes, so that is certainly one way to see it. It's not vague, okay? But I'm, as I said, I'm not going into the geometrical picture today, though it's very important for proving a lot of things, okay? That this is equivalent to the identity system in some sense, and so on. But can we explain this algebraically for now? Not just algebraically, it's like combinatorially. Yes. Yes, so we are making a row transformation. But why does row transformation not change? That's the same thing. Why does it not change the solution? Right? That is the thing. So it's very simple. I think all of you kind of already know it, but let me just say one side clearly. I think once I say that, the other side will be also clear. Yeah, so as people are already seeing, we should look at the corresponding matrices, right? It's better to look at the corresponding matrices. This is not needed for me to explain this, but this will be useful because now we will also then look at this matrix as a function and whether the function is injective or not, that will tell us whether there's a unique solution or not, and so on. So you'll see. So sorry, today I'm a little unwell. Just one minute. So this B is 2, 1, 1. Okay. Yeah. So then what? So how do we explain that the solutions are the same? Okay. So well, if x1, well, there's a very straightforward way. Okay, I should just say like this: if x1, y1, z1 is solution of this side, I mean, then obviously when you add two equations, like, so basically what I'm saying is there will be, I'm first explaining this in the, very non-technical way. This, and then when you add equations, then obviously again the same thing will be true, right? That is because when you, that's, yeah. So that basically proves that the solution of the, but that's not a very enlightening way to do it in, because you'll see. Right. So that is certainly true. This, so certainly true that solutions of A is contained in solutions of B. Right. But how do we go the other way? Okay. And before you say or think, let me also say it via matrices. Can anybody say it in terms of what I've explained now is solutions of A, because all this will help you to get those, this, which we'll do later, get them naturally from now. So I wanted to explain solutions of A is contained in solutions of B via matrices. I mean, it's not a good question maybe, but yeah, same thing, same thing. So you can, so say through functions. How do you say through functions? So A is the function. A, I don't know. A is the function. Why? What's wrong with A? Right. No, do you agree? I'm not trying to make you agree like that. I'm just saying, is it okay to consider A as a function? Exactly. Exactly. So A times, and then you can continue, or anyone should, can say, should say, um, A times, it's all very simple stuff, but we're just doing it. A times x1, y1, z1 is 0. Okay. We want to show that B times x1, y1, z1 is 0. I mean, if you're in, if you're like in high school, like, and if you don't, let's say, then you would rather convert this into a matrix question and answer. Sorry, you would rather convert this matrix question into a system of equations and answer this question. Do you guys agree? Right. You would rather do this than say it to, but we are trying to take it one step forward, right? So let's see. Can anybody explain this conceptually? How this would imply that this is 0? I've already explained it in one way, but I just want to see if we can say it in another way. Okay. Yes. So why must it preserve this preserve this solution? Because I'm doing a combinatorial operation, right? I'm kind of switching rows. In this case, I'm subtracting one row from the other. So why should this combinatorial operation preserve solutions? But then you're giving the equation thing picture. Yeah, right. Yes, but that's again in terms of equations you're saying more or less. Right. Um, am I right? Huh. Ah, okay. Yes. So say, yeah, that's interesting. Capture row. So, okay, first of all, let me just say this row operation statement. What is the row operation? We are subtracting, we are replacing the second row by was first row minus second row. That's how this is coming. Okay. Okay. Capture row operations by matrix by just matrix. Okay. One second, someone is joining. Who is joining? Okay. Your brother is joining, Sampath. Okay. Good. Okay. So Sampath, before you say, let me just concretely say this. Okay. This thing clearly so that also for Haridatta who has just joined, he can also get the like because there's a problem basically that we are trying to solve, small problem. So let me remove this. Yes, and I didn't start. I mean, I didn't open that thing which you had sent me about using that writing thing. I'll do that. Maybe I should do that at the end today and next time. Okay. So what we are trying to do is capture this row operation by matrix multiplication. What does that mean? We are trying to say find a matrix E, just calling it E. Find a matrix E such that E times A is equal to B. So A and B is in front of all of us, and B is gotten by subtracting. Okay, you can see you take the first row, subtract it, and you get this B. Now, can you find a E? Okay, before someone tells how to find the E, do you guys understand that if you find the E, then the job is done? Or if you can show that there is such a E, right? Because if you can show that there is such a E, then we are done, right? Because A times x1, y1, z1 equals to 0, which is what we have here. That will imply that E times A of, I mean, obviously, right, no doubt, is also equal to 0, which is basically B. So then we'll be done. Okay. So now can we find the matrix E? So let's think. I mean, I'm saying it like this because all of you know matrix multiplication. Otherwise, this is a very good way to even introduce matrix multiplication. But since you guys already know, and then I don't want to introduce it in a different way because it just, yeah, so. Yes, that is what matrix multiplication is. And that's the combinatorial view of matrix multiplication. That's just the word I'm using. Right. So then what should this E be? Okay, nice. 1 minus 1, 0. No, this is not correct. I think, yeah, you are meaning the right thing, but you're saying the wrong thing. I think it should be this, I suppose. Ha. So this is, I mean, obviously, maybe all of you don't see, I mean, you can check, but what is the explanation? That this times A is equal to B. But how did he get that? Okay, right. That is okay. So how can we generalize this? So let's try to see matrix multiplication as combination of rows. So when you are, yeah, so right now I'm explaining this thing. So like conceptually, how you would get this. So see, I mean, if you have a matrix like, so let me not write the whole matrix, okay? But what I'm really interested in is the rows. So we have R1 and we'll just treat R1 as one piece. I mean, it's the same thing, but you see it just moves, you know, the whole row moves together in some sense. And so we have R2 and similarly we have R3. The applications of this interpretation go everywhere, you know, permutations, transpositions and permutations, combinatorics, everywhere. I mean, just this is just very good thing because we are encoding some combinatorial thing into an algebraic operation. That's very, very, very advantageous. We're looking at this. Now suppose we just multiply this by a row. Okay, let's say you just multiply this by 213. So what is it going to do? Okay, what is this going to do? Obviously, this will return me a row. This is going to return me a row, right? But what is that row going to be? If you treat the first row as like a vector, right, then it's going to just do 2 times that vector, right? It's going to do 1 times the second row and 3 times the third row. Now you understand, if you just multiply, you will get the same thing. If you do your usual rule multiplication, which that rule is derived from this. I mean, we put that as a rule because it's a very useful thing to do, but when we practice it a lot and then we apply it when we do engineering. But here we should understand it because we have to also use it in interesting ways and things. Okay, so we are doing 2 times this first row, 1 time the second row, and 3 times the third row, and that's how we get this. Just to show it in an example, if you do 1 1 0 and yeah, so let's write some numbers. Okay, so I mean we can, yeah, so we can, yeah, okay. Now, so I thought we just take this this matrix itself so that we can see how, you know, we won't get the transformation, but we'll get some other transformation that this thing. So you see, and you will agree that you'll get the same thing. So you when you multiply this with this, what are you doing? You're taking 1 times this and you're taking 1 times this and 0 times this. But when you multiply this with this, you do the same thing. So why not do it together? That's all I'm doing, right? So I'll do 1 times the first row and 1 time the second row, and I just add, and 0 times the third row. And so when I add, I mean, I'll get, this is basically R1 plus R2. But what will that be? So you understand this is R1, this is R2, R3. This will be very essential. So we should understand this even very computationally so that it's very, very clear. Because you have to see some computational situation and predict this operations in more elaborate places. So yes, 5 minus 1 and 8. Okay. So is it cool, right? We are taking linear combination of rows. I mean, that's how you get the first row. And obviously the second row is, you know, so what happens? So if what will this do? This will tell you the second row of the output, right? And this will tell you the third row of the output. Okay. So everything in the output matrix, right? When you multiply this matrix with this matrix, then you get 3 rows, right? The first row in that output, this first row is completely, the first row is a combination of the rows of A, and how to combine them is given by this 100. This means take 1 times the first row, don't take anything else, and that's the first row of the output. And similarly, this tells you what to do with the second row I mean, sorry, this tells you what will be the second row of the output. You know, so any questions? Yeah, any question? And surprisingly, this is the only thing, I suppose. I mean, other than that, other things follow from here very easily. Okay, most things follow from here. Interpretation. So if there are any questions, then please say. Otherwise, we'll just move forward. Okay. So there is a more abstract view that you are taking vectors and you're taking linear combination of those vectors. Okay, I will do them later, not with all of you. All of you don't need it. I will ask and select, and also ask those who want to and select, and the people who are. So we will discuss it there. There's a more abstract view in terms of vectors. So they are basically vectors. We're taking linear combination of vectors, linear independence, and so on. But those we are not going to do in this class. Okay, because that's too much, not very useful in most cases. Right. So now okay, my point is that now any kind of row operation can be captured by matrix multiplication. So that's what we have proved, right? Now by any, I'm not going to classify and tell you all the three, right? What are the row operations? Okay, any row operations can be captured by matrix multiplication. But I will be giving some interesting questions about these row operations. So can anybody formally tell me what are those row operations? There are apparently three of them. So when you're taking a matrix or a system of equations and then you usually do these three row operations, which also don't change the determinant, or they change, they change, but in a very smooth way. But adding the rows and subtracting the rows is the same thing. Okay, so yeah, so one is that taking a linear combination of rows. Yeah, so basically I'm saying replacing a row Ri by so it's what's a simple way to say it. Yes, right. K1, I'll say K. KRI plus JRJ. Okay, so actually I don't need to say this. 1 second now. I can just say replace this by, and I'll ask you to prove why this thing. Okay, I'm not multiplying Ri because that will be captured in a. What is the next one? The next one is to just multiply the row itself. Okay, this is there, and these two are different the way I've stated. And what's the third one? Permute the rows. Okay, so that I will just say as swapping rows, right? So switch Ri and Rj. Okay, so these three. Now I want you to show that two of these are enough to get the third one. And that has some very good implications, but for now, I just try to prove that the two of them are enough to get the third one. Okay. I mean, at least that's what I think is true. Yeah. In a different context. Yes, exactly. So that's why these topics which we are doing, it's also we'll see that Gaussian elimination. It's useful in solving, but it's also such algorithmic reasoning will be needed. So it's a yeah, that's how it is. It's holistic. So two of these are sufficient, but this goes into very interesting thing later on, that you can get from one row if there are two equivalent matrices, which means they have the same solutions, then you can go from one to the other, not by any matrices, but we say matrices with determinant one, some other subgroup, so on. It's very interesting things come up, but for now we'll just prove this. So this is a problem, okay? Try to see. Just take 3 rows and do it. And so you may need several of them. Like you may, like for example, to get 2 using the others, you may need to apply the others in several times. I don't know what you think. So for all these operations, we have corresponding matrices, okay? So if you want to take a matrix and you want to apply one, let's say operation 3, then there is a matrix which you can multiply to the left and get it. Okay, I'm not describing those matrices because I explained the general thing. And yeah, you can think about those matrices. But now I'll also ask some questions, but now show the reverse. Yeah, that's a pending question. Show the reverse. I'll remove this soon, so you can note it down or you can watch it later, but show the reverse. So we want to show that solutions to 2 are also solutions to 1. Solutions to any solution of B is also solution of A. Yes, okay, so you can do the same kind of thing. So you can, again, for B, you can find a matrix A, which will get you to A. So for B, you can find a matrix E, some other matrix, which will get you to A. Okay, but can anybody explain this combinatorially, right? Because this process is reversible. I'm just saying, the process is reversible, right? I mean, you're not losing anything. Is that good? Yeah. If you are so. Mhm. Yes, because at each step it is invariant. At each step you don't lose it. Yeah. So can anybody tell me just quickly tell me the reverse of this thing? How would you go back to system 1 by doing a row operation? Just for this context, just for this thing. Okay. Is that right? No. Something like that, but that's not right. Yeah, you have to subtract maybe. Yeah. So I'll just say, because this is simple. So you see, so basically what you have here is, again, just saying it. Okay. So this is R1, this is R2. But essentially these process, like, like swapping and all is obviously reversible, but this is also reversible. Yeah. So what do you have? You have R1, and this is R1 minus R2, and this is R3. So you can obviously reverse, right? You have to just subtract from the second row, you have to subtract the first row, and then you have to multiply the second row by minus again, right? So wait 1 minute. Like for each row operation, we define an inverse. We define an inverse row. Yes, exactly. Yeah. So that is certainly what we have to do. Maybe you can do that for homework, but I'm just explaining it in this particular situation, and it's just the same idea, right? Like for each operation, you could define an inverse operation. Okay. So what are we going to do here? We are just going to take R1, and maybe we can do R1 minus this, right? So this is just the inverse, and you can always do this. Okay, you have to do a 1 by k and so on. Okay, but remember, we need division to do this. Okay, we need division. sometimes, right? I mean, if you are taking, so if you have like R1, or maybe just like Sampath said, we can actually try to do this. So let's say you're replacing R1 by R1 plus 2 times R2. Okay, and R2 and R3 are as they are. Now can somebody define an inverse of this process? In terms of this, obviously, in terms of the same row operation language. This time there is a 2 here. So R1 is getting replaced by this. So if you want, you can call this your R1 prime, R2 prime, and R3 prime. R1 prime minus 2. Oh, yeah. So this doesn't need division. Sorry. Yeah. R1 prime minus 2 R2 prime. Right? This is what we have to replace R1 prime with. Then you get R1 back. Do you guys agree? It's just the, just do the opposites. Okay. Right. And similarly, when you multiply a row, you have to divide. You have to multiply a row by a constant, then you divide the row by the constant. That's where you need division to reverse the process. Okay. So then it's very simple. Now let's just take a few seconds break. Let's see if someone has any questions. Because grasp this very carefully, because we are going to do some tough questions. In a sense, some very deep, it will have some deep consequences, but for us, they're just problems to begin with. We'll do. You'll have to do. Okay, good. Let me ask a question. So for those who have not yet said anything, okay, so those are like Raghav and Sampath, so you two will know this, but I just want to ask this question, the others also. Suppose it's very simple, okay, so don't worry about anything. It's very simple. It's just 1, 2, 3. So just the matrix. And I did this row operation of swapping. Okay, and I get this. Can you find the E? Okay, so only to the ones who have not yet said. Okay, so just because I just want to make sure that we're all comfortable with this. We have shown the reverse. We have shown. Yes, I don't want you to answer. I mean, I wanted to answer, but not now. After, if no one else says. Yes. So, what matrix should you multiply by? What should be the matrix that you multiply by to get it directly for the swapping to happen? So, next, we will see how we can apply these things to get to, for any system, we can go to a simple form. And from there, it will be very, since the solutions are not changing, from there, we'll be able to comment on the possible types of solutions. Okay, so what should be the matrix that we multiply? No. So there will be no -1, right? Because you're swapping the rows, right? In E, in E, there should be no -1, right? Okay. So let me try to say it from the way I've explained, and then I'll try to say that in a different way also. Whatever you want to do, whatever you want to do to this matrix, do that to the identity matrix. Okay. So you want to swap the rows, first row and second row of this. Then you take the identity matrix and swap its rows. Okay. And that's all. This will do it. You can see it in another way. Okay. All of us can see this, I'm saying, in another way. And what is that way? Yes. Yeah. So can you explain? That would be good. Hmm. Okay. So we don't. So for the output, this is becoming the second row, right? So I want to take 0 times the first row. I want to take 1 times the second row, and I want to take 0 times the third row for my output, for the first row of my output. Okay. So that's what it is. I mean, obviously, you can also take X. You can also just take 9 variables and solve equations and get the answer. It's not going to take a long time actually. Okay. I mean, one can just take 9 variables, right? X, Y, Z, and just multiply this and get this and then solve some small equations. Okay, but that's not going to be very insightful. Okay. In fact, that's how some of those Olympiad system of equations which have very quick solutions are made. And these are one of the ways it's made. There would be others, obviously. Okay, so now do we all of us understand? Yeah, that these can actually be done. Okay. Okay, so now let us see. 1 second now. I want to ask a question. Yeah. Now I want to ask this question. Let's say that I give you this system, the same system, okay? The same system. And yeah, you can take X, Y, Z. And yeah, something ABC. Okay. So if, sorry, second. If sorry, yeah. So if, so what I'm trying to say is that if A of X, Y, Z equal to 0 has a unique solution, okay, then show that AXYZ equal to ABC has solution for each for each ABC. I could have given you some special matrix and asked the question. You can take some if you want. You can take this, and I think this works. But let's try to answer this question. Okay. So let's say if I told you that this equation has only one solution, okay, then I'm saying that for any ABC, there is a solution, XYZ. And for this, it's just free. You can, if you know, you can use geometric thing to also get the intuition or whatever. Just try to do this. Let's see. And this is a fair enough problem, right? It's not some very abstract problem. Yes. So what should that unique solution be? Removing this thing. And also I'm removing this B now. This B is not important. This B matrix now. That was just a sanity check, kind of what we always do, subtract equations and so on. So what should that unique solution be? Come on, it's unique. Come on, it's a so A of so this thing has a unique solution. There is a unique XYZ which makes this 0. So what is that XYZ? Yes, so that is a 0, 0, 0, right? So there is no, I just gave it like that. Okay. Because I mean this can be said in other general ways, but this said, okay, simple. Now, how do you show that everything will have a solution? Change meaning you have to change XYZ. Obviously, you can't change A. Yeah, so solution means that you have to, yeah, you have to find an XYZ. So yeah. So is a question clear to everyone? Right? When I say solution for each ABC means that if any ABC I give you, I could give you I could have given you a concrete when I asked this question and there would be this clean answer. There would also be a calculation answer based answer, but that's a different thing, right? Um, yeah. So I give you an ABC, you give me XYZ, and the claim is that you can do this for any. And I'm not asking you to solve the equation and actually tell me. Okay, because well, this is an abstract question in that sense. But even if it's for this particular one, yes, yes. Wonderful, right? So that's one approach, but that is a slightly, let's think that is certainly an approach. So the whole problem is now show that A is invertible. This will just do the whole problem. But I've yet not introduced the concept of, because, but obviously all of us know this, show that A is invertible. So this will certainly do the problem. Yes. Um, yes. Everything. So this entire problem, I'm just basically was going to introduce this as a motivation for invertible matrices, but that's not the point. I mean, you can use this if you want. How do you show that A is invertible? That is not so simple, right? Because if A is invertible, then these things are easy to prove. But showing that A is invertible, yes. Mhm. Exactly, exactly, right? So if you show that A is injective, then it is surjective. So we are not going to, I mean, let's not directly show that this is invertible. There are good ways to do that, and this is what we will do when we come to this simple form of a system of equations, which is also very important, okay, to solve problems and to further go into theory. But I wanted to use this to I wanted to apply the function theory that we had. Okay, so let us see. Okay, so let me just put that as a hint, and I suppose especially those of us who have attended the class on function view, because then you have the language to say it directly. But any obviously can try to say, so view A as a function, A as a function. So what is it as a function? A is a function from R3 to R3. Okay, and if I'm saying that A of X equal to 0 implies X equal to 0, right? We have proved that this implies that A is injective. But someone please do that, prove it again now. This is a wonderful, this I had even given as a problem. Just this much implies that A is injective. Someone please recall the proof for me, or yeah, just prove it. Yeah. Yeah, right. Mm-hmm. Okay, 1 minute. So I will just use a, because this x1 may, so this x is a vector. Okay, so I'm not going to write the y, just write like this only. Okay, so this means it's a column vector. So all this means it's a column vector. Okay, because yeah. Okay, then we, yeah, so then you got it. I just subtract it. Yeah, and then we are done. I mean, x is not equal to y, right? But so it means that if A is not injective, then you have a non-trivial solution. So we are done, right? Okay, but this part I want you guys to pay attention, because this is a very strange property, but then it's also a very ubiquitous property. It just keeps coming all the time. So what is this saying? It is saying that injectivity, to prove injectivity in general, it is enough to kind of prove injectivity at 0. Okay, so translatability of statements. Okay, we want to prove something in general injectivity, but we're just proving injectivity at 0. You agree that's what it is, right? Ax equal to 0 means A of 0, x equal to 0, right? A of 0. So injectivity at 0 is enough. And this will just happen in all linear or linear kind of places. Whenever you feel in a kind of place, this kind of thing you should expect. Whenever you have an inverse, okay, so you can bring the things to the origin and do the argument, this kind of thing will be there. Okay, so this is a very good property. And now we have also proved that injectivity implies surjectivity, but I'll also try to review that. Maybe we'll come up with a different way to say it. So A is injective. Is there any questions with that before I move forward? That why A is injective? Okay. Mm-hmm. Yes, yes. Huh? Yes, yes. Yes, yeah. So the out means every element in the codomain can be attained. Yeah. So that is, so this language is not new in the sense that the basic theory of function, the basic functions language that we have, injective, surjective, I'm using it in the same way. Okay, but we are getting this new good condition for injectivity. This you don't get if your thing is only a set, right? Yes. Yeah, that's right. So we have not proved it in this class, but we proved it in the earlier class, but we're going to prove it again. And maybe we'll, as I said, come up with a different proof. Yeah, but I have proved it earlier, but let's do it again. Means sense get something new. So everything boils down to, okay, why did I remove that? So that's the worst thing to remove. So now let us show that injective is surjective. Okay, so see, injective is not always surjective. Sorry, I mean, that's number one. And number two, you do not always, so I'm just rephrasing the same thing again and again, because see, injectivity, I mean, all of us know this, that f of x1 equal to f of x2 implies x1 equal to x2. This is what injectivity is, right? That if f of x1 not equal to x1 not equal to x2 implies this. Okay, this we all know. But, and obviously this also means that f of x equal to 0 implies x equal to 0. For 0 goes to 0 type of function, you understand, yeah? But this will not imply injectivity. This itself will usually not imply injectivity. We have another structure of addition and subtraction in the picture, which we are using to say that this implies injectivity. We have a structure of subtraction in our system, and this function is mixing with that subtraction structure well. That's why we're getting this simple condition. Okay, so in places where it doesn't happen, you won't get this, but in many places where you expect you won't get, you will get this condition. In polynomial theory and many differential equations where you can kind of subtract solutions and so on, you will have these kind of things popping up there also. Okay, so look out for these things. This is a good thing. Obviously, all this can be said in a way that all those situations can be put in one language, but we don't want to introduce that. Okay, so there's a message. So now you guys try to prove injective is surjective. Yes, exactly. As long as it mixes with the structure. Okay, so yeah, as long as it mixes with the structure is basically the same thing. Yeah. I mean, this even extends to topology. Like all the neighborhoods around 0 is the same as the neighborhoods in any place, which is obviously true in R2 and so on, right? Yeah, but anyways, so now we want to show that injectivity implies surjectivity. And this is pretty easy. We had shown this last time. I mean, this can be made hard, can be made to look hard, but we had kind of done it in an easy way. And Chandan, so the problems I had sent you, I think today's discussion will solve those problems. Is that right? Yeah, you try them again. Okay, I think today's discussions should solve the problem. Yeah, but linearly independent. Oh, you've already done. Okay, then we'll just discuss it in the end. It's good to discuss them. Yeah, we'll just do it after this. I just give a few problems to try, but that you'll do for homework. So come on, someone tell me. Injective implies surjective. We had explained this in a very nice way, and also, yeah, interesting way. I think. Yes. Hmm? Yes, linear combinations. Yeah. Yes. No. So that's basically that's. I think that's all I had said in a different way. But yeah, it's okay. So same thing. So basically, we won't take any linearly independent set, but let's see. Let's try. Okay. So we have this injectivity, and we want to get surjectivity. So we have this E1, E2, E3. So you guys know what this is. Okay. So let's write it. This is 100 because we want to see this, and this is 0. This is such a fundamental thing. There is only one way to do this. In some sense, but they are all not just logically, but they are same in some sense. You see, so there are these things, and let's say A is a function. A is injective. Okay. A is injective. So what do we want to say? We want to say that these three things don't lie in the same plane. That's what I had kind of proved last time, right? That these three things are not in the same plane. So these three are vectors, right? These three would be some vectors. So there is a computational version of this thing which is called rank nullity, okay, which actually tells you how much of what goes to 0 and how much is remaining and what we start with and connect them through numbers. But yet now we have not defined those numbers, and it's hard to define them rigorously and prove that they are dimension, which we'll not do now. But what I want to you guys to see is that these three are not in the same plane. Because of injectivity, they are not in the same plane. Okay. Am I right? So what do you mean by not in the same plane? I mean that these three vectors are not in the same plane. Not so. I'm not saying so. I'm not saying that the endpoints are not in the same plane. Okay, you should understand that. I mean the vectors. Okay, the vectors through the origin, those line segments, they are not in the same plane. That's what it means, right? That's what we want to prove. Not in the same plane. Can anybody show this first? That injectivity implies this? Hmm. So what does it mean to be in the same plane? I mean, it just means that two of them, when you take a combination, so this we had explained, right? You get the third one. I mean, it's not necessarily this will happen, but some two of them will give you the third one. Just like, yeah, if there are three vectors which are in the same plane R2, then obviously you can use this and this to get this middle one, and you can use any two to get the third actually. Right? You can take linear combinations of two of them and get the third. I mean, it's just very obvious. You know how to, what to do, right, to get there. So this we had explained. So just you can think about this if you can get this, and then obviously, I mean, if they are in the same plane, you get this. But this is obviously a violation of injectivity. So do you see why it is a violation of injectivity? Yeah. Because uh, yeah, you can take minus C3, or basically you can also get this, right? But obviously this two, I mean, this can never be equal to E3 because again, they are in different planes, right? They are orthogonal. So two of them, you cannot use them to get the third. So they are different and they're going to the same place. So it's not injective. So that's a contradiction, right? So basically three vectors, if they are not in the same plane, then the output would also not be in the same plane. I mean, when there is injectivity. But obviously, if these three things are in different planes, then again, you can get any fourth vector using this. You can even see how to kind of move to get there. So yeah, in the end, I am using some geometric ideas. Basically, using that any three vectors which are not at the same plane, then those three you can use to get any fourth vector. Okay. Yeah. And it's not difficult, right? Because you can take the planes that are formed by, let's say, this plane by EA1, EA2, and then this plane, and then this plane. And you can kind of project this new vector on those planes, right? And those projections will give you the, you can use them to combine them to get this. Maybe we had explained this for R2. That's why it was very simple. So just see if this is okay. Yeah. It is not, no, so it is surjective because, yes, because now we have shown that these three are not in the same plane, right? So if these three are not, so what I'm saying is that if three vectors are not in the same plane, then you can use them to get any vector. Otherwise, one can go full blown into matrices and then determinants and so on, right? Invertible, but then it's the same thing. To do a rigorous proof, one has to introduce the concept of dimension and so on. Okay, but you see, if there are these three vectors in the output which are in different, which are not in the same plane, then it is, I mean, it's okay, right? You can reason this that you can use these three vectors, so you can magnify these three vectors appropriately, or demagnify them, shrink them, and you can create any vector. Right? I mean, you can even describe a combinatorial. You can describe that process, at least in R3. Okay, you can describe that process. You can. That's not difficult, right? That's all I'm saying. And since these three vectors, let's call them W1, W2, W3, since you can use them to get any vector, so it means that it is surjective, right? Because then you can get anything in the image, right? Okay, because I mean, if you have, let's say, 2, 3, 5, and you can get them from W1, W2, W3, let's say by taking 2 times this and not taking W3, these are again vectors, right? Then you know that this is coming from E1, this is coming from E2, so from this, you will get this, and so you can get, right? So yeah. So basically, when you take these three things in the image, then you can also take linear combinations of them. They will also be in the image. Okay. So yes, yeah. So this is what I want to say. So let me then give a question. Maybe this is a good question to think about. So the first question is, if A and B give same solutions to Ax equal to 0, Bx equal to 0. So if A and B are two different matrices, but their set of solutions to is equal to 0 is the same, then I want you to show that there is a matrix E. So it's an extension of this row operations that we have done now today, such that this is equal to B. I mean, what we did one row operation, so solutions were same, and from there and we got a matrix E. But now any two matrices, so this is like the reverse, right? Any two matrices which give the same solutions, means they have the exact same set of solutions. Okay, any solution of this implies solution of that, and so on, and vice versa, not so on. Then I wanted to show that there is a matrix E which you can use to get from one to the other. Let's see if you can do this directly, then we can use this to get to what we want. And if you cannot do this, then we will get to where we want and then prove this. So we'll see, because there are so many ways to do these things in the sense that so many different looking ways, but there's always some non-rigor in each of them if not done in the properly. So this is one of them. And I forgot what was the next question I was thinking. So let's clear this and then we'll just discuss the problem. So let me clear this. We'll discuss those two problems. So 1 minute. I have a question, but we have not yet discussed the things to be able to do that. This one you can do, but okay. So let's get to that. So let's save this, and so you can try this. Then I will get to. Okay. So there are two problems which I want to discuss. They're pretty easy, just for practice, mostly. I mean, yeah. So I'm just sharing this thing only, and can do from here. Okay. So so all of you may have not seen this problem. So just try them for maybe 5 minutes if you have time. Yeah. I think we are already above time, but just try them for 5 minutes. I'll just come back. Okay. I'm having a little bit. Okay. Try them. All of you can see the questions. No. Can you see? Yes or no? Ah, yeah, that's why. Yes. Because when I stopped share this thing, then I have to start it also. No? That's why I asked. Should have said. Now you can see. So these are just simple questions in the sense, but we should all do this. And then I'll just come back. Just try them after 5 minutes, 10 minutes, 5 minutes, try them. So you guys have the question. Let us discuss. Let us just discuss it here only, right? You can just write things here. I can write. So who will do the first one? Who will say the first one? Yes, yes. Anyone? Okay. Uh-huh. Mm-hmm. 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 Uh-huh. Okay. Right. Okay. And then you kind of computationally showed it. Okay. So yeah, so that is working out. That is good. Hmm. So yeah, so you computationally get it right. Uh, okay, I've written the rows are dependent. No, I think you just multiply these two, and whatever you get, you show that you can find some lambdas for that also. The same lambdas will work, right? No, no, no. I'm not writing the rest of it because it's clear, right? If you multiply this with this, oh, okay, okay, sorry. Okay, that thing. Okay, no, no, I did write some things. Oh, you can't see. Okay, so that is not feature is not there then. So then I will just go to the whiteboard and do it. Okay. So this is a problem. You can try this, but yeah. But no, but let's do it in a conceptual way. Okay, that solution which Chandan you have given, you see that were you able to generalize it for 3 cross 3? Well, you can, but it will just take more time. Right. Multiplying out everything and so on. Yes, yeah. So you should, yes, anyone, yes. Let me just write the question quickly, a little bit in short. So if columns or rows, same thing, columns of B are linearly dependent, then so are that of AB. Okay, yes. So somebody you want to say? Okay, that's good. Yeah. Okay, because I didn't share. Yeah, that's what happens. I didn't, yeah, stop sharing and I didn't share this one. Now you can see. Now it will come. Yes. Mm-hmm. Huh. Yeah. So let's consider 3 by 3, though it's not important, but just for explanation purpose. Yes. So you are saying that, see, so linearly dependent means that there is some linear combination which makes it 0, right? That means lambda 1 times C1, lambda 2 times C2, plus lambda 3 times C3 is 0. What do you mean by 0 here? Because usually in high school, we are used to 0 being a number here, but this 0 is a vector. Okay. So this is 0, 0, 0. So just to point this out, so Chandan, you were using also linearly dependent but you were using it in a, like you broke it up into the coordinates and you were using, right? that there is one lambda 1 which will, right, work for all the 3 coordinates. Is that right? Yeah, let me say expanded and say, so it is, because that is a distinction, right? We introduce vectors and we introduce vectors addition so that it mimics this linear combination thing. So that when you take linear combination of several things by the same weights, then that can be said at once. And that's why we introduce, that's why the addition is made like this, right? So that's what we want to exploit. We don't want to break it up and say. So let me just say this point. So when you say these two are linearly dependent, what do I mean? I mean that there is one lambda such that lambda a this thing over lambda 1, lambda 2, this is 0. And we also say, hold on, what am I doing? The columns. So yes, so this is right. Yeah. So then lambda a22 is 0. And what does this what does this mean? This means that a11, oh my god, what am I doing? Yes, yeah. So you can column, yeah, I should write it as a column. That's then, otherwise it's just more confusion. Yeah. But what we are trying to do now is we're trying to use this language of vectors to do our arithmetic, to do our linear combination. We want to just say that this is 0. These two are the same things. Okay. These two are the same things, right? But now it is just like single addition, it's kind of taking care of that. Okay, and that's how we should interpret it, right? Linear combination of columns means that you're taking this column, taking a weight, and then this column taking a weight, and the addition is 0. And then there is another way, which is this break it up and do. But don't think that this break it up and do is an inferior way. No, sometimes when we are doing some hard problems, like we have to do take transpose and so on, you have to break it up and do, and then you have to consider row wise and so on. So both things exist, they're equivalent, and they have their own things. Okay, so that's what we are doing here. Okay, we are taking the linear combination of the whole column at one shot by the same weight, because that's what it means. We don't have to break it up and say it will not help us in our argument here. Okay, so then what? Yes. So basically then that's the solution to the system. Okay, so you look at B as this coefficients of the system, right? And this becomes a solution to the system. Okay, then what? Non-trivial solution, right? Same will hold. Yes, right? So if this times this is equal to 0, I mean, that certainly implies that AB times lambda, okay, lambda you can write as this, is equal to 0. I mean, that is obviously. Yes, right? Whatever those columns are, that's what it means, that they will be linearly dependent. Okay, but just to say this once again like this, if there are some other, you get some other columns, C1 prime, C2 prime, C3 prime, right? Basically, you have to again see matrix multiplication on the left is like taking linear combination of rows. Matrix multiplication on the right, this is basically taking linear combination of the columns, which I've already basically used earlier, but this is what, and you can see, you can compare this with your usual multiplication, which is a very unfortunate way to, I don't know why it's done like that. Why it's introduced like that. It is same thing formally, obviously, but why it's done like that is not very insightful. Maybe some commentary is useful, but yeah, this is what it is. You see, it's a, when you multiply, then you take the linear combination of the columns. You take lambda 1 times this column, lambda 2 times this column, and you get this. That's the result. That's the column you get as the output. And you can just check this with your usual multiplication. Okay. And then so we are done. So you see how the system of equation view just does the problem so quickly. Okay. Is it clear to everyone? Chandan, you see the difference in this technique? Okay, so this is the usefulness of connecting these things. Okay, so then let's discuss the next question. Yeah, let's discuss the, yeah, and also, okay, what is that? Let's do that. Mm-hmm. 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 Lambda 1 square plus lambda 2 square. No, I mean, okay, if you're over reals, then it is not 0. Yes, so you're saying lambda 1 square. Okay, yeah. Okay, fine. So let's take okay, let's take this, not 0. Hmm. Over the reals. Okay, so I mean, obviously we assume that these are over reals. Yeah. Though being over reals is surprisingly not a good thing in this theory, but for now we assume it. Yeah, no, but yeah, but in this case it is reals. I mean, this exams obviously it's real. Yeah, so it's fine. Uh, okay. A times C1. Uh-huh. Yeah, that's how it should be. That's what it is. Sorry. Yeah, exactly. But let's see if does everybody see this? So this is the first column of the output. Absolutely. Yeah. That's again a wonderful way to. So let's see if everybody sees this. Yeah. So just think, right? When you're multiplying with A, then how do you get the first column? You get when you compute the first column, you don't use this at all. Right? Just from your, if you take the most computational view also, right? You do like this is A, right? So you do this times this, then you get this cell, right? Second row, first column, second row of the first column, and so on, right? And then you understand that it is just like taking A and multiplying with C1. That's how you get the first column. Sorry. Okay. Okay. And you can also see this from the row view and so on, but this is a better direct way to see it and see it. Okay, then what do you do? It's very interesting. Uh-huh. Mm-hmm. Mm-hmm. Yes, yes, that's right. So you can take the A out. That's perfect. Yeah. Wow, nice. Oh, this is nice. I mean, this is wonderful, right? If we did we use this square, this lambda one square, and so on? Okay, then it is just better to say that, I mean, one of them is not zero. Yeah, okay, never mind. The same thing. Yeah, yeah. Yeah. No, at least one of them is not zero. Yeah, at least, yeah, same thing. At least one of them. That's the meaning of linear combination. Otherwise, everything is linearly dependent. Okay, so you see, so you guys see, right? Just this different views of matrix multiplication. So this I had not thought of. I mean, I have already, we all know this. Like if you tell you, you know it, but I had not thought of this, right? So this, there's different ways of viewing matrix multiplication can do so many things for us. Okay, I think it's very good. We will also see a computational view of this. Um, but no, sorry, a computational, a quantitative version of this, where we will see that if the largest number of linearly independent vectors in B is, let's say, 10, if there are n number of columns, then in this also it will be at most 10. And that you guys can already see, but I'm not giving this as a homework. That is not for now. Let's develop things gradually. So let's go to the next question. Okay, before the next question, I remembered one question, so you guys can try this for homework. So suppose you have this A11, A12, A13, A14, dot, 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 dot. Okay, so there are 4 rows this time. No, so 3 columns only, but you have 4 rows. So you have A41, A42, A43. Okay, so you can understand there are 4 rows and 3 columns. And I have this, oh, hold on, what is happening? Sorry, huh? I just want 2 rows. Sorry. Just a second. Anyways, yeah. So you take 2 rows. Okay, so if you have this equal to 0, okay, show that there are infinitely many solutions. Okay, yeah. So show that there are infinitely many solutions to this. Let me just think if this is correct. For any, you can take any and do, but show that there are infinitely many solutions. Yeah, right. So this should be correct. I mean, yeah, geometrically it is certainly correct, but also if you can give a reasoning based on the kind of things we did. But either ways, you can do this. Okay, so let's do the next question. Today we are having a slightly longer class. Okay, fine. We will have the next class maybe after 2 days. So let EI denote the column vector with 3 elements. Okay, so we know what EI is. Okay, now you have this linear transformation which takes E1, E1 goes to E1, and so this is L is just a matrix. Okay, L is just a matrix, and that's what is happening. This is going to this, and E2, E3. Okay, so then the question is L surjective? I mean, or this is a matrix. Okay, so yeah, is L is from is L surjective? Right? So, okay, so since you know the answer, let's see if, so we all know the answer is yes. Can anybody else explain this? Let's see. Okay, like what? Like row transformation to what? Okay, okay. So you are saying that you will take a matrix like this, identity matrix. Is that right? Is that what you're doing? Okay. 100. 100. But what is the initial matrix? That is identity, right? Or is it? But you need to have a matrix to start with, right? Or is that right? I mean, you need to have something matrix to start with, isn't it? So this is the matrix to start with, right? And then you are doing R2, replacing R2 by R1 plus R2. Right. Okay, so that's what L is already doing. Okay, so E1 transforms to, okay, E1 is going to E1. Are you transforming E2? Okay, so E1 you're transforming to, yes, but you're doing R2 plus R1 to what? To what matrix? I mean, row transformations have to be applied to some matrix, right? So that's what I'm saying. You have these three vectors you're starting with, and then you're doing the row transformations, right? I I mean, you understand. Otherwise, R1 plus R2 doesn't make sense. Where is R2? The R2 is the E2, right? So is that right? I mean, otherwise it doesn't make sense, right? So you have to say that there is this matrix, and to this I'm doing the row. Basically, these three vectors, I'm just arranging them like this, and then I'm doing the row transformation. Okay. So then what happens? Okay, then say, okay. E1 is E1. E1 is what? E1 is 100. Okay. Second row. What is second row? Which second row? This vector. I don't understand. This vector, okay. Hmm, transform it to E1 plus E2. But then that's a column operation. Are you doing a column operation, or I don't understand. So can anybody else try to explain this what he's saying? I didn't understand. Huh? Yeah, I mean, without a matrix or collection of vectors, how will you? Yeah, Yeah, or you can say that L is doing that. I mean, L is doing that, but L is doing that. Huh. Yes. Okay. So then, yeah. So then so Chandan, then I don't understand completely, but yeah. So then let's try to do something similar to what you have done, or then you can write in because I didn't understand it. Okay. But let's see. So we just do something similar, right? Uh, so uh, can anybody say or any other method? Let's see. Or then I'll try to say something similar to. I'll say that in the end, maybe. Yes. So what will that be? Yes, we want to show L is surjective. Yeah. Not injective. Yeah. So we will show that L is injective. That's the. Uh, yes, that's what we want to show. Right. Hmm. Yes. Yeah. So only 0 goes to 0, or Lx equal to 0 implies x equal to 0. They're all same things. Okay. Mm-hmm. Okay. Okay. So let L times lambda 1, lambda 2, lambda 3 go to 0. Right. E, uh-huh. Lambda 1 E1. Yes, so this is what we should explain. Yeah. So this thing basically means, so lambda 1 E1 lambda 2 times E2 plus lambda E times E3 goes to 0. Okay, so this is what it means. Some input goes to 0. Okay, not injective means some input goes to 0. And this means, so just say this means basically that lambda 1 times LE1, which is just E1, lambda 2 times E1 plus E2, right? And lambda 3 times E2 plus E3 is 0. Okay, so does everybody understand it till here? Is this part okay? Okay. And so, but this is not possible. You can just check this. I will not do this. Okay. Not possible because you can just, you know, take E1 common and so on. Okay. So not possible because E1, E2, E3 are independent. That is clear. All right. So you can, that is a contradiction. Okay. The other way to do it, I mean, you guys can just, I mean, just solve linear equations, right? You just take this and you will end up with a matrix, right? So you can make a matrix out of this. Okay, maybe that will get complicated. So this is okay. Let's see, someone has an alternate way to do this. I can think of a different way. This is, yeah. Yeah, so similar way. Okay, so then maybe that's similar. Yeah. Basically, the point is that, look, these three are in different planes. You can see this, right? I mean, those three outputs are in different planes. You can see, right? They are not in the same plane. draw, you can see, because you know what happens in vector arrays. So if they're in different planes, then they will generate everything. Okay, so that it is surjective basically. Okay, well, maybe one slightly different way can be which the idea I'm getting from what Chandan is saying about row transformations. So I'm saying, look, you start with this matrix, okay, and you do basically what is being done here. Okay, so I'm like, okay, so this is a matrix and E2. So I mean, E3 is getting replaced by E2 plus E3, right? So I'll do R3 is getting replaced by R2 plus R3. Okay, and once I do that, I get what? I get this, right? And then what happens? Okay, then I'll have to do another transformation, right? Where R3 gets replaced by R2 and so on, blah, 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 right? If you just do another transformation, right? I mean, R2 gets replaced by R1 plus R2. And then you will get the right matrix and 1, 1, 0, 0, 1, 1. Is that right? You get, so you come from here to here by row transformations. What does that mean? If you, this is the identity matrix, but let's call it A and this is B. It means that with A, you multiplied some that corresponding row transformation matrix, and then you had another one which you multiplied and you got the B. Okay, what is this B? This B is essentially what L is doing. Is that right? Right. This B is essentially what L is doing. Right. So whatever L is doing, we have done that to the rows of B. Right. So if you multiply something on the left of B, what you get here, this is basically what the output of LX will be. Okay, maybe you'll get it as rows and something like that. Okay, so yeah, but maybe this point is not so clear to everyone, I think. Yes, but yeah, but it's slightly in a non-traditional way, right? So I started with the identity and then I multiplied with this transformation and got here, but then I multiplied with another one and I've got here. And this is what L does, but to the column, but to the rows. Usually we write it as column. So let's not, this is actually just confuse people, okay? So let's not do this because yeah, that will lead to some big confusion. So let's not do this, let's leave this. Yeah. So then we are done. Then we are done. Yeah, let's stop here. Okay. Let's stop here. We'll meet not tomorrow, maybe on Friday. I'll try, or if I cannot, then I'll do on Saturday, definitely. Okay. And yes, I will install it. It got deleted. So just send by a mail, then I can install it.